Welcome to The Explainer. Today, we're popping the hood on the artificial intelligence revolution. By 2026, AI has really transitioned from this playground of experimental models into a regime of pure industrial-scale deployment. But the systems that are simulating global climate patterns or running these massive billion-parameter language models, they don't just run on magic. They run on incredibly heavy, highly specialized underlying engines. These are the deep learning frameworks processing all that complex AI math. And choosing the right framework today, well, it's not just a casual developer preference anymore. It is absolutely crucial. It's a foundational architectural decision that dictates your scalability, your hardware costs, and honestly, your long-term success.
To really understand where we are right now, just look at this staggering number, 85%. That is PyTorch's dominant share in deep learning research papers today. Think about it. If a new, cutting-edge foundation model or some totally novel neural network architecture is being built in a lab somewhere, there's an overwhelming probability it's being written in PyTorch. It is literally the undisputed heavyweight champion of the research frontier.
But, the story doesn't end in the lab. Contrast that huge research dominance with this figure, 37.51%. That is TensorFlow's commanding enterprise market share, and it's being utilized by over 25,000 companies globally. So while PyTorch totally rules the academic papers, TensorFlow remains the entrenched backbone of legacy industrial pipelines. It's out there moving models reliably to billions of users every single day. And that dynamic sets the stage for a massive structural rivalry.
Okay, let's dive into this. Here's our roadmap for today. We'll hit the 2026 AI Trinity, then PyTorch, dynamic by design, TensorFlow, the static heavyweight, and JAX, the functional frontier. After that, we'll look at hardware synergy and performance, and wrap up with the ultimate decision matrix.
Starting with Section 1, the 2026 AI Trinity, from chaotic proliferation to industrial scale. Moving right along to Section 2, PyTorch Dynamic by Design, subtitled The Researcher's Eager Engine. So why exactly did PyTorch win the research war? Well, largely because it lets developers write models exactly how they think about them. The core architectural decision that made it so famous is the dynamic computation graph. You might also hear it called eager execution. Basically, instead of compiling this massive mathematical map ahead of time, PyTorch builds the execution graph on the fly right as your Python code runs. Why does that matter? Because it means you can debug your AI models just like normal code. You can drop in a simple print statement or use standard debugging tools right in the middle of a computation. And when the whole AI field pivoted to complex data-dependent transformer models, this dynamic flexibility turned out to be incredibly prescient. But, as you might guess, that kind of flexibility historically came at the cost of pure performance. That is, until PyTorch 2.x dropped and introduced Torch Compile. This was a real game changer. With literally a single line of code, developers can now wrap their eager mode model in a compiler that generates highly optimized kernels using Triton. This delivers massive 30 to 60% speedups without forcing anyone to change how they actually define the model. It effectively turned PyTorch into a fast-moving production stack, beautifully bridging that gap between research agility and real-world production speed.
All right, Section 3, TensorFlow, the static heavyweight, also known as the enterprise production giant.
Listen, there's this persistent myth floating around that TensorFlow is somehow dead just because it lost the research crown. But what actually thrived is its role as a production giant, and that's all thanks to its historical superpower, the static graph. This is an architecture where the entire computation graph is fully defined and compiled via the XLA compiler before any execution even happens. Now sure, it makes debugging a little bit more challenging, but it allows the compiler to basically see the whole board. It fuses operations together, it eliminates redundant memory copies, and it optimizes kernel execution globally. When you're out there running massive inference clusters across thousands of CPUs or GPUs, this static efficiency is exactly what keeps your throughput high and your costs manageable. And this brilliantly illustrates why, when you step out of the lab and into the real world, enterprises just refuse to let TensorFlow go. It's not just about training anymore. It's about keeping a model alive in the wild. You've got TensorFlow Extended, or TFX, managing end-to-end data lineage and MLOps. You have TF Serving handling battle-tested, high-throughput model deployment. And then there's LiteRT. You probably know it as TF Lite, which is an absolute juggernaut, quietly running machine learning on over 2.7 billion edge and mobile devices worldwide. TensorFlow is just built for the rigors of the real world. Which brings us to Section 4, JAX, the functional frontier, the compiler-driven wildcard. Now, JAX isn't really a traditional framework at all. It's more of a compiler-driven wildcard, built strictly for extreme, close-to-the-metal performance. But to use it, you absolutely have to embrace functional programming. Think of it like an incredibly strict math teacher. It requires pure, stateless functions and completely immutable data. That means a function's output depends solely on its input with zero hidden side effects, period. JAX demands this strict purity because its underlying XLA compiler needs to trace the entire computation graph to optimize the math globally. If you had random states mutating mid-trace, the compiler would simply break.
Notice the stark architectural paradigm shift here. Over in PyTorch, you can freely mutate a model state in place, just say A plus equals B, and you can rely on global random number generators. JAX outright forbids this. State is locked down and immutable. You must explicitly write out A equals A plus B. Even random numbers require explicit key splitting. So yeah, it demands a much steeper learning curve, but the payoff, it's immense.
The real magic with JAX happens because these 4 core primitives seamlessly compose together. You can use JIT to compile a function straight to fast machine code. You can use GRAD to automatically compute exact mathematical gradients. You've got VMAP to automatically vectorize a function, and PMAP to instantly parallelize it across multiple devices. Because they all nest together so cleanly, JAX unlocks a massive structural advantage. To put that into perspective, in areas like reinforcement learning, researchers using JAX are seeing up to 1,000x speedup simply by running the entire simulation loop on device.
Moving on to Section 5, Hardware Synergy and Performance, where software architecture meets silicon. So the crucial point to remember here is that software alone doesn't define speed. It is ultimately constrained by your silicon. Let's look at the hard data. NVIDIA's H100 GPU is the universal workhorse, right? Perfectly synergized with PyTorch, delivering around 1,000 peak T-flops per chip. But it's pulling a massive 700 watts to do it. Contrast that with Google's TPU v6e. Because TensorFlow and JAX compile natively to XLA, they can directly unlock the TPU's architecture. This delivers a really competitive 918 T-flops, but at a highly power-efficient 300 watts. So if you're out there doing massive cluster-scale training, aligning JAX or TensorFlow with TPUs can deliver up to 4 times better performance per dollar. That is huge. But hey, what if you don't want to be locked into just one hardware or framework path? Enter Keras 3. Honestly, this is one of the most underrated tools out there right now. It basically acts as the Switzerland of AI. It's a completely back-end agnostic bridge. You can define your high-level model in Keras and literally switch between PyTorch, TensorFlow, or JAX as the underlying back-end with just one line of code. It provides an incredible migration path that really minimizes technical debt write-offs for organizations trying to modernize.
Let's wrap things up with Section 6, the ultimate decision matrix, aligning architecture to your goals.
So what does this all mean? How do you actually align these complex architectures to your specific real-world goals? Let's break down 3 common scenarios. If you're a Series A founder building a fast-paced AI startup and you need rapid prototyping, novel NLP models, and instant access to the latest Hugging Face research, PyTorch is for sure your engine. Its dynamic graphs just let you move fast. Conversely, if you're running AI infrastructure for, say, a massive healthcare insurer serving millions of patients, you desperately need the static reliability, the strict data lineage, and the edge deployment capabilities of TensorFlow's TFX pipeline. And finally, if you're a research lab training neural surrogates for climate simulation or doing massive-scale reinforcement learning, you need the functional purity and that sweet TPU synergy that JAX provides.
As we wrap up this explainer, I want to leave you with a question to really chew on. Is your current AI framework structurally aligned with your team's objectives? Or are you just quietly building infrastructure debt? Look, the days of casual framework tribalism are totally over. By deeply understanding the real under-the-hood realities between dynamic graphs, static compilation, and functional primitives, you can intentionally choose the exact engine required to power your specific vision. Thanks so much for joining us on this explainer, and we will catch you next time.